of the problems in your text are going to involve functions of 2 variables, so I wanted to just quickly work through one example with 3 variables, because this notion of finding a local linear approximation applies to functions of more than one variable. Okay, so I've given us a function of 3 variables. Remember, we would say that the output is a w value, so the graph of this would be in 4 space. We call the graph a hypersurface in 4 space. And then I've given us a point. P naught is 2, negative 1, 0. And I want to first of all find the local linear approximation at P naught, and then use that to estimate the function at a point that looks like it's relatively close to P naught. Now here, I'm using the name local linear approximation. Sounds like we're supposing that this function is differentiable. I can actually see that it is. Now, I'm not going to use the definition of differentiability because that involves evaluating a limit that would be pretty tricky to evaluate in this case. But I can see that this function is continuously differentiable with respect to all 3 variables. And as long as the partials exist at and near this point and are continuous at this point, that's the criterion we have for checking very quickly whether a function is differentiable. Okay. So I'm going to need to know what f of P naught is. So if we plug in 2 is 2, negative 1 squared is times 1, e to the 0 is 1. So I'm going to get 2 times 1 times 1. We're just going to get 2. That would be the w value at the point of tangency. What we're calculating, by the way, with this linear function, algebraically, it's just a linear function. It'll be some x's plus some y's plus some z's plus a number equaling our w value. Geometrically, we would call it a tangent hyperplane. It's almost like a tangent copy of 3 space, but it's kind of hard to visualize because it's tangent to this hypersurface in 4 space. Okay, so let's get our gradient. I know that's just the vector whose components are the partials with respect to x, y, and z. Partial with respect to x is just y squared e to the z. This with respect to x is a constant by which I was multiplying by x. Partial with respect to y will be 2xy e to the z. The x and the e to the z are constants. Partial of y squared is 2y. And partial with respect to z will just be xy squared e to the z. These first 2 factors are constants, and of course the partial of e to the z with respect to z is e to the z. So if I take a look at the gradient of f at 2, negative 1, 0. Let's see. Negative 1 squared is 1. E to the 0 is 1, so we're getting a 1. 2 times 2 times negative 1, we've got a negative 4. Times e to the 0 is 1, so negative 4. And then xy squared e to the z, we'd already calculated. That was actually just 2. Okay. Fabulous. So now I can put together my local linear approximation. That's going to be L of x, y, z will equal the w value at our point of tangency, which was 2, plus our gradient at the point of tangency, which was 1, negative 4, 2, dotted with the change vector. So that would be x minus 2, y plus 1, z. All right, excellent. So that gives me my equation. Let's go ahead and work it out so that I don't have any vectors in it. Generally, when I'm writing an equation that's giving me numbers, I'd like to not have any vectors in it, so I'll work out that dot product. So that's just 2 plus x minus 2 minus 4 times the quantity y plus 1 plus 2z, if I do that dot product. And I think I'm going to go ahead and simplify that so that I can consolidate all of my constants. So that would be, let's see, x minus 4y plus 2z, just going through and collecting the variables. And then 2 minus 2, those are going to cancel. And I'll distribute that negative 4. I already got the negative 4y, now I'll get a negative 4. Okay, so that is my local linear approximation. Okay. So now we wanted to use that to estimate our function evaluated at 2.1, negative 1.01, and 0.02. Now for that, it might almost be simpler to work with this version of things, because there that has me calculating x minus 2. I'm looking at just how close is that to 2. And y plus 1, how close is that to negative 1? So I think I'm going to go ahead and actually use this version of the equation. So what we're doing is we're saying f of 2.1, negative 1.01, 0.02 is approximately the same as L of 2.1, negative 1.01, 0.02. And that would be 2 plus x minus 2, we're plugging in 2.1, so that's going to be the 0.1, minus 4 copies of negative 1.01 plus 1 would be negative 0.01, and then plus 2 copies of z is plus 0.04. All right, so a little bit of arithmetic to do. 2 plus 0.1, that's going to be plus 0.04, plus 0.04. So that's going to become 2.18. You'll notice the w value at our point of tangency was 2. This 0.18 that we ended up adding to the 2, that's the result from this part of our equation. And in our next video, we're going to start talking about that as we start talking about the notation and the vocabulary of differentials.